This is the first section of Chapter 6 Game Theory, and in this section we're going to be looking at play safe strategies and stable solutions. So let's imagine that you're playing a two-player game, so you're playing against somebody else, and both yourself and the other player have a variety of strategies to choose from. So there are different ways in which you can play the game. And let's say that each strategy will win or lose you a certain number of points or even money. Well, we can represent all of this information in what we call a payoff matrix. So here's an example of a payoff matrix. So here's our two players, player A, and player A is always written on the side like this. And player B, they're always written along the top like this. So you can see player A has two different choices, two different strategies they could pick in playing this game, whereas player B has three different strategies they could choose from. Now the numbers in the brackets that look like coordinates represent the amount of money or points that each player wins. The first number represents what A will win, and the second number represents what B will win. So for example, if we looked at this box here, so this would be when player A plays strategy 2, we just say that A plays 2, and when player B plays their strategy number 2 as well, we say that B plays 2. In this scenario, A would win 7 and B would win 5. Let's have a look at another cell instead in this matrix. So let's say we looked at let's say the very first cell here. In this case, A plays 1, B plays 1, so A would win 2, so that's less than if they played 2 and B played 2, and B would win 5. We'll look at one more, and we'll have a look at this very last cell here. So this is where A plays 2, B plays 3, A would win 5, B would win 4. Now the choices that A and B make will depend on whether they know what the other player is going to do. In some cases they don't know what the other player is going to do, so that's going to affect their choices. Also what's going to affect their choice is if they decide to collaborate. So A and B may get together and say, right, let's play this particular strategy, whichever one, because it benefits us both. So it may be that they collaborate and A plays 2, B plays 2, because that's going to sort of benefit both of them. And they can have some sort of discussion about which cell they're going to, or which strategy they're going to play. Now, assuming that player A and player B don't collaborate and they don't know each other's choices, they may decide to play safe. Now, playing safe is an example of what we call a pure strategy. Now, pure strategy is where each player is going to play the same game every time. So let's say A decides to play 1, they're always going to play 1 on every sort of time that they play the game. And playing safe is like saying, right, whichever I play, let's say A decides to play 1, they don't know what B is going to play, they're going to play the option that gives them the least worst outcome. So let's examine this in a bit more detail. So let's look to see what happens if A plays 1. So if A plays 1, they could win 2, 4, or 3. The worst that can happen is if A plays 1 is that they only win 2. So let me put 2 down at the side here. Not sure why I'm doing it in that pen. Let's do it in this pen here. So 2. So that's the worst that can happen if A plays 1, because they don't know what B is going to play. If A plays 2, they could win 3, 7, or 5. The worst that can happen, because they don't know what B is going to play, is that they only win 3. So based on this matrix, A may decide to play 2, because it doesn't matter what B plays, the minimum they're going to win is 3. Whereas if they play 1, the minimum they're going to win is 2. So they're always going to win a little bit more if they play strategy 2 or A plays 2. And what we've actually got here, the one that we picked, the 3, I should actually only pick circle the 3, is the maxi min. So we've looked at the minimum values across all of the winnings, the points that it could get, 2, 4, 3. I picked the minimum of those. I picked the minimum of 3, 7 and 5, and then out of those two minimums I picked the maximum. So A would pick a strategy where it gives them the maxi-min, the maximum minimum possible wins. So let's have a look at player 1, or player B, sorry. So player B, let's say that they play 1. Now this is assuming they don't know what A is going to do. So B could win 5 or 1 if he plays strategy 1. If he plays strategy 2, he could do 1 or 5. Strategy 3, if he plays 3, 6 or 4. Now, if B plays, they don't know what A is going to do. What could they win? They could win 5 or 1. So the minimum they're going to win is going to be 1. Across here, the minimum they're going to win here would be 1 as well, if they play 2. And if they play 3, the minimum that they're going to win between 6 and 4 is going to be 4. Why have we picked the minimum? Because we're thinking about each player playing safe. So if player B plays safe, they're going to pick strategy 3, because it doesn't matter what A plays, they're going to win 4. Whereas in the other choices here, they're only going to win 1. Now, the winnings in this payoff matrix could also be written in a different way. So let's take out what B is winning, and we're going to change it to something called a zero-sum game. Now, in a zero-sum game, whatever A wins, that's exactly what B loses. So I will change some of these values. So I'm going to take some of these out here. And let's start with the first one. So in this first cell here, in a zero-sum game, so now this is changing to something called a zero-sum game. And it's called a zero-sum game because the total winnings in the cells will add up to 0. So in this one here, if A wins 2, that means that B loses 2. 2 minus 2, 0. Hence the name zero-sum game. Let's make up something for this one here. A playing 1, B plays 2. So this time, let's have it that player 1 could lose 4, which means that player B would gain 4. And the same thing here, if player A wins 1, player B loses 1. So this is another way in which the winnings can be shown. One person's gain is the other person's loss. So let's complete this bottom row here. So this completed matrix now shows a zero-sum game. So let's say that both players are not collaborating. They're using a pure strategy of playing safe, which means they don't know what the other player is going to play, but they're going to they want to choose a play, either 1 or 2, or for player B, 1, 2 or 3, that's going to give them the least worst option. So let's look at player A playing 1. Now if they play 1, they don't know what B is going to play. They could win 2, lose 4 or gain 1. So what's the worst that can happen? They can lose 4. So I'll put -4 here. Okay, how about if they play 2? Well, they could lose 3, gain 1 or gain 6. So what's the worst that can happen? They can lose 3. So what should player A do? Well, they should play 2, because the worst that can happen is that they lose 3, whereas if they play 1, the worst that can happen is that they lose 4. Okay, so if player A plays 2, what we've got here, this -3, as before, is the maxi-min of A's possible winnings. So we go along the row, we write down the minimum of each row, and then we pick the maximum of the minimum. Okay, let's go across now and do the same for player B. So if player B plays 1, what's the worst that can happen? Well, they can lose 2. What's the worst can happen here? They can lose 1 if they play 2. And if they play 3, the worst that can happen is that they can lose 6. So again, what option should player B pick? They should pick the -1, because that again is the maxi-min. But there's actually redundant information in this table. I've got A's winnings and B's winnings, and sometimes those winnings are negative. If I know, let's say I take these out and just have the single number 2, it may be that I know that actually, well, whatever B gets is going to be the opposite to that. So let's take these out. And what we've got now is a zero-sum game. But this time, nothing is written down for B. These numbers represent what A is going to get from their perspective. We know then that B is always going to be the opposite of that. So we know this is going to be -2, this is going to be +4, this is going to be -1. So we can see a payoff matrix written in this form where there's just a single number here, and this single number is from A's perspective, A's point of view. Now that doesn't change the maxi-min, the options that A can take, whether they play 1 or 2, it's still going to be this maxi-min here, -3. I mean, we could fill in all the opposite numbers in this matrix, but by picking the mini-max, we can actually work out what the best option is for player B. So let's work out the mini-max. So for each column, I'm going to work out the maximum value, which actually would be the minimum for B. So this time the mini-max. So we look at the maximum value in each column. So the first one is 2. Second maximum is 1. And last column, the maximum is 6. Now the mini-max of 2, 1 and 6 is 1. So player B should play 2. So what we've got here, this is like B losing 1. This is like B losing 2. This is like B losing 6. So by keeping just that single number and working on those single numbers, if we work out the mini-max, then we have the option or the choice that B should play. So in this zero-sum game, the best option for player A is to play 2, and the worst they could lose is 3. Whereas for player B, they should play 2, and the worst that they're going to lose is -1. So remember, this 1 represents what A wins, so they would lose 1. So just remember that. These numbers are from A's perspective, from their point of view. So B's point of view is going to be the negative of these values. So this is the same payoff matrix that we had before. Now we're going to be looking at something called stable solutions. So we've got player A playing 2, because this is their least worst option. They don't know what B is going to play, so the worst that can happen is that they lose 3 if they choose strategy number 2. And player B also playing 2, because their mini-max, which is what we've worked out, so the worst they could lose here is 1, whereas they'd lose 2 here and they'd lose 6 here. But the players may have an incentive to change, because they may have an idea of what the other player is going to do. So for example, player B, they decided they're going to play 2, and the worst that can happen is that they're going to lose 1. But they may have some sort of idea of what A is going to do, and they may have decided they may be better off moving to strategy 1 or playing 1, because at least they're going to win 3 here. So they may take a chance and take a bit of a gamble and change strategy. And they may have an incentive to do that, because playing a different one may give them a better deal, a better option. Now, if neither player has a reason to change, it's not going to benefit them. This is what we call a stable solution. And this is one where neither player, player A or B, has an incentive or reason to change their strategy. Now, we can tell if a payoff matrix will have a stable solution because there'll be a stable solution if the payoff matrix contains something called a saddle point. And the saddle point is going to be one of these cells in the payoff matrix. And a saddle point is where we have a cell where the row maximin is equal to the column minimax. So the row maximin, this value here, is equal to the column minimax. Now this one doesn't have a saddle point at present, but I'm going to change the values so it does have a saddle point. So this payoff matrix now has a saddle point, which is this cell. I changed this value. So the minimax is -3 for player B, and the maximin for player A is also -3, and those coincide in that cell. So this is what we call a stable solution. So if A plays 2 and B plays 2, they have no incentive to change to a different strategy because they're not going to improve their winnings or their points. So the row maximin, which is got here -3, is equal to the column minimax -3. Example 1. In this payoff matrix, player A has a choice of 4 options and player B has a choice of 3 options. The outcomes are given as ordered pairs: A's winnings, the first values, and B's winnings, the second values. Determine the play safe strategy for each player. Now, since this is not a zero game matrix, their winnings are different, we want the minimum for each row and column, and then we'll take the maximum of those values. They're playing safe. What's the least worst thing that could happen? Right, so let's start with player A. They could win 8, 0 or 7 if they play 1. What's the worst that can happen? That they win 0. If they play 2, they could win 3, 9 or 2. What's the worst that can happen? They could only win 2. So remember, they don't know what the other player is playing. If they play 3, player A plays 3, they could win 1, 6 or 8. The worst that can happen is that they win 1. And if A plays 4, they could win 4, 4 or 5. The worst that can happen is that they only win 4. Let's look at the same for player B. Look at the column minimums. So they could win, if they play 1, they could win 2, 6, 7 or 2. So the worst that can happen is they win 2. The second column, the worst they could win is 0, nothing. And in the third column, the worst that they could win is 1. So both players want to play the least worst option. They don't want to play the worst of the worst option. So for player A, what's their least worst option? Well, it's going to be playing 4, because if they play 4, the minimum they're going to win is 4. The other options are not as good. And how about player B? What should they play? They should play 1, because the worst that can happen is that they only win 2. So let's write that down. So we have player A playing 4, playing row 4, and player B playing column 1. Now if both players decide that they're both going to play safe, that means we get to this cell here. A will win 4 and B will win 2. Now it may be that if they collaborate and they sit down and decide beforehand what they're going to play, they may increase their winnings by collaborating. But in this case, they're playing safe. They don't know what the other player is doing. Example 2. Determine the play safe strategy for both players, A and B, for the game below. So this is a zero-sum game given from A's perspective. So if it was for B, this would be -3 here, 4 here, 2 here, and so on. So we need to start by finding the row minimums, which we'll do in a moment. and then also the column maximums, because this is now a zero-sum matrix. So if we start with the row minimums, we have in the first row -4, second row -2, third row -3, last row -1. And we want the maximin, the maximum of those minimums, and that's going to be -1. So that came from the bottom row. So playing safe, A should play 4. And for B's perspective, because this is a zero-sum matrix, it's from A's perspective, we need to do the opposite and find the column maximums, which would actually be B's minimums. So the first column, the maximum is 3, second column maximum 4, third column maximum 4, and we want the minimax. Because this is from B's perspective, everything is the opposite. So the minimax would be 3 here. So minimax is 3. So B should play 1. So let's see what would happen if A and B both decided to play safe, and A played 4 and B played 1. So we'll just highlight those. So A plays 4, which will be here, B playing 1, which would be here. The intersect of those two cells is this one here. So if they both played safe, that means that A would win 1 and B would lose 1. Example 3. Anna and Ben play a two-person zero-sum game, which is represented by the following payoff matrix, which is here. What we need to do is to find the play safe strategy for each player and show that the game has a stable solution. So let's start by finding the row minimums and the column maximums. So the row minimums, first row the minimum is going to be -1, second row minimum is 3, last row the minimum is -2. We want the maximin, the maximum of the minimums, which is 3. So there's our maximin, which tells us that A should play 2. So A plays 2. Right, let's work out the column maximums, and they are 4, 6, 3 and 7, and we want the minimax, which is 3. So minimax, and that means that B should play 3. So B plays 3. Now we also need to show that this game has a stable solution, and it does, because the row minimax is equal to the column maximin, and it's 3. So this strategy here. So neither player has an incentive to change. So the way we'd want to write it is that there is a stable solution since there is a saddle point, because the row maximin, which is 3, is equal to the column minimax, which is also 3. We would say that the game is in equilibrium. There's no change. It's a stable solution. Or we could add that by the stable solution theorem, there is a stable solution. I guess there's always a stable solution when horses are playing this game. Example 4. A two-player zero-sum game has the following payoff matrix for player A. So these numbers in here are from player A's perspective. First thing that we need to do is to show that there is a stable solution. So the first thing that we need to do is to work out the row minimums. I'll write those down. Then the column maximums. So the column maximums. And let's start with the minimums first. So the row minimums are -4, -3 and 5. Our maxi-min is 5, so maxi-min is equal to 5. Let's look at the column maximums. So first column maximum is 7, second column maximum is 5, the last column maximum is 6. We are looking for the mini-max, and that is also 5. So the mini-max is 5. So the way that we'd put our answers is this. Since the row maxi-min is equal to the column mini-max, which is 5, by the stable solution theorem, there is a stable solution. Okay, let's have a look at part B. And part B says, find the value of the game to A. Well, if they're playing safe, then it would be this same value here. So the value of the game to A would be 5. To B, it would be -5. So the value of the game to A is 5. Nice and easy. Example 5. A 2-player zero-sum game has the following payoff matrix. What we need to do in part A is determine the play safe strategy for each player. So as before, we want the row minimums and we want the column maximums. So the column maximums. So let's work those out. We'll write those down. So the row minimums are -2 and -5. So the maxi-min is -2, maxi-min, and the row maximums are 4 and 3. So the mini-max is 3. So then we have the mini-max. So if each player is playing safe, then A would play 1. So A plays 1 because that's where their maxi-min is. And B would play 2 because that's where their mini-max is. So A plays 1, B plays 2. Part B, it says verify there is no stable solution for this game. There'll only be a stable solution if the row maxi-min equals the column mini-max, and it doesn't. So by the stable solution theorem, there is no stable solution. Let's write that down. Part C, it says state the payoff for each player if they both play safe. So let's have a look to see which cell that's going to be. So A plays 1, so it's going to be in this row. B plays 2, so it's going to be in this column. So it's this cell here with the -2 in. So let's just highlight that. This cell here. So the value to each player. So remember, this matrix is from A's perspective. So A will lose 2, -2, and B will win 2. And lastly, part D, we're asked to determine the payoff matrix for B. So our matrix is going to look like this. Now everything now is from B's perspective, so we'll put player B over here to show that it's from their perspective. And now we need to look at what their winnings will be. So here, if B plays 1, so if B plays 1 here, they would lose 4, gain 5. So they're playing 1 now goes across rather than going down. So B plays 1. From their perspective, if A plays 1, they would lose 4, and if A plays 2, they would gain 5. So rows become columns, columns become rows. The values get reversed as well. In terms of matrices, this is what we call when we transpose a matrix, when we swap the rows and the columns, but these values also reverse as well. So B plays 2, so it's going to be these column of numbers. So if B plays 2 and A plays 1, they will gain 2 because B is losing 2. It's a zero-sum matrix. And then the last value here, if B plays 2 and A plays 2, A gains 3, which means that B will lose 3. So you should now be able to do exercise 6A on pages 118 to 191 of the textbook.